Okay, so maybe we start. So this is the fourth of these lectures. And so I've told you about this TUT recursive description of maps, of planar maps. And so this afternoon we'll make the only incursion to the non-planar world. So I have to tell you, when she's smiling, so I have to tell you in advance that I'm not normally a higher genus person, but I'll do my best to give you an idea of what can be done for maps on a torus with holes, with several holes, by applying this same idea of TUT, delete the root face and look at what's left. So essentially what I'm going to present is some parts of a paper. So that's maps of higher genus. And I will follow a paper by Bender and Canfield, which I think appeared in '86. So this is more recent than TUT, but not extremely recent, as you realize. So they do something, it's a bit more complicated because they consider the case of non-orientable surfaces, which we won't consider. So we'll just have a torus with G holes. And so I told you that this approach was robust, and I want to convince you that it is indeed robust, can be applied here, and allows you to compute inductively the generating function of planar maps on a G torus. So far, I have only defined maps on the sphere. So the first thing I have to do, obviously, is to define maps on another surface. So here, again, it will be just orientable surfaces, compact, no boundaries. So this is really the G torus. So something like this with G holes. Okay, so map on G torus. So it's again an embedding of a connected multigraph And for the planar case, this was your definition, but here you want to insist that the faces, which are the connected components that are left when you delete edges and vertices, you want these pieces to be disks, to be homomorphic to disks. So every face is a disk that is homomorphic to a disk. And again, all this is taken up to orientation preserving homeomorphisms of the surface of the G torus. So this is what I will call the topological definition. This is not the one we're going to play with. But still, I'll take one example. So say on a torus, we could have two vertices. And so maybe there's two edges like that. There's maybe one loop attached here, other loop here. What else? I had something slightly more complicated, so maybe I'll try to reproduce that. should make the hole a bit bigger. Sorry, I hear complaints. I should start from scratch. Okay, let's make a big hole here. You see why the topological definition is not simple. So I want what? So I think that's the example in Guillaume's Chapuis thesis. I want two loops. Where does it go? Oof. And then I want an additional thing going here. Should I use colors for the edges so that you distinguish them from the hole? Two vertices, a loop attached to each vertex. And then this additional, I have 3 edges in total joining the 2 vertices. And then I should add that these maps as well will be rooted as we had in the planar case. By choosing a corner that is an incidence between a face and vertex. So for instance, this is my root corner. And if I'm brave enough, I should try to look at the faces of this thing and try to convince myself that they are disks. So let's try to do this, not that I am being very optimistic. So, okay, so let me try in the root corner, and I'm following sides of edges. So I start, say, here. So this in orange is supposed to be the boundary of a face. So here, I follow on this side, come back here, if I'm not mistaken, go on here, here. Now I am on this side here, back here. So it seems that I have a first face here. Okay, then what? Maybe in blue. So let's say I start from this corner here, 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 here. Following this one, now on the other side. So I have a second face here. And there would be a third one, which I leave black, which is here and there. Okay, so let's say this thing has 3 faces. Okay, so I hope I've convinced you that this is not very easy to play with. Yeah, this is something we can do, and in fact, I want to have this Euler formula, which tells you that the sum of the number of vertices and faces is equal to the number of edges plus 2 minus 2g. So how many vertices do we have here? We have 2 vertices. I claim we have 3 faces. And in terms of edges, we had the 2 loops and then 3 edges between the 2 vertices, so that was 5. So v plus f minus e is 0, and so it's consistent with the genus 1. Now the other definition, which will be more convenient for what we do, is the so-called combinatorial definition. of a map on the G torus, and in fact on a map on some G torus. And so in this definition, what is defined is not just a map, but a map with a labeling of the half edges. So if you have n edges, you have 2n labels, and precisely labels 1, 2, up to 2n for half edges. So maybe I'll take rather a planar example to tell you what we do with those labels. Simple case. So say we label say the root half edge will be labeled by 1 always. So this is my root half edge. And then I spread labels on half edges. So 2, 3, 4, 5, 6, 7, 8. We need to label 10, 11, and 12. So I have 1, 2, 3, 4, 5, 6 edges and 12 labels. Okay? I need the 9. I forgot the 9. How could I do that? Is that better? Yeah. Okay. So given this intuition, we now define a combinatorial map on 2n half edges is a pair what's the usual notation? Sigma and you should know that by heart, and alpha, which are permutations in the symmetry group. So permutations of my 2n labels, and you want some conditions such that. So alpha is an involution with no fixed point. So what will alpha be? It will describe which half edge is matched with which other half edge to form edges. So here, so one edge is 1, 2. If I go up to 3, we have 3, 9. Then 4 is matched to 11, 5 to 7, 6 and 8 here form the loop. And I still need 1, which is 10, 12. So that's one of the, well, that's the involution corresponding to this planar map. And there's no special condition on sigma, but in fact, okay. And then the final condition is that the group generated by the pair alpha and sigma, it acts transitively on the set of labels. So I tend to denote integer intervals between square brackets like that. So I should tell you what sigma is, what it means on those topological maps For this, I need a bit of space. So we had said that alpha describes edges, and sigma, it describes vertices, and more precisely, the incidences of those labeled half edges with vertices. And to describe that, you need to choose some cyclic order around vertices. So for instance, here around the vertex, I would read labels in counterclockwise order. So let's do that. So there's a cycle of sigma corresponding to this vertex, and this will be the cycle 1, 6, 8, 11. So there's as many cycles in sigma as you have vertices in the map. Then say I move to this one, which has just degree 2. So the length of the cycle is the degree of the corresponding vertex. Then I have a 312 here, and then a final vertex where I have, sorry, it's not final, there will be this one. So I have 4, 9, 5, and finally 7 is by itself. So that's my sigma. So now this final condition, the fact that these two permutations act transitively, just tell you that the map, the graph is connected, that you can go from any half edge to any other by moving along edges and turning around vertices. Okay. So what should I add? So now Euler's formula tells you that certain, I should describe, sorry, I'll get back to that just a bit later. I first want to tell you how you read faces out of sigma and phi. So say you want to describe some face, so we have defined sigma as going in this direction around vertices. So which face am I going to describe? So if I want to describe this face, I'm turning here. So say I start here, I have some label I. Here I have alpha of I, this other label, and then I turn here. So what I have here is sigma alpha of I, the vertex of this half edge. And in fact, if I define phi as the permutation sigma alpha, this is the permutation that describes faces. That is when I go around faces and read these labels, I get, they are described by sigma alpha, if I'm not mistaken. So I repeat, I start from I here, this is alpha of I, and since sigma goes in counterclockwise order, this one is sigma alpha of I. So now going back to Euler's formula, what it tells you is that the number of vertices, which was the number of cycles of the vertex permutation sigma, plus the number of faces, which is the number of cycles of phi, is the number of edges, which is n, plus 2 minus 2g. So you see that in this definition, there's no explicit reference to the genus. So here is how you can compute it from your sigma and alpha, or equivalently from sigma and phi. Yep. Yeah, so I'm coming, so far now we have two definitions of a topological map on one side and of a combinatorial map on the other side, and I clearly need to relate them. That's, of course, the next point. So what happens is that, so how could I describe that? So if I take, so combinatorial maps taken up to permutation of the large labels they are equivalent, using this construction, to topological maps. So you notice that I fix here the label 1 for one edge, and this is for one half edge, and this is equivalent to fixing the root corner. So in other terms, if I leave the 1 here and relabel everything else, well, here, of course, I get the same map, but this is the connection between the two. So when you have this definition, you do not need a surface. You do not need to see the surface. You do not need scissors to check that your faces are faces, and this is much more convenient. So if I say this maybe more roughly, it says that a map is a connected multigraph where the order of half edges around each vertex is important or recorded, or you have to remember the order of incidences of half edges around vertices. And so the equivalence between these two things is nothing obvious. So it's proved in some basic books that you can find the references of in Guillaume Chapuis's thesis. So there's apparently, for this theorem, there's a paper by Brian Mohar and Thomason. It's not a paper, it's a book called Graphs on Surfaces. And Guillaume also cites, and I've not checked, I trust him, Massey's book on algebraic topology. I'm certainly not going to prove this, but what we'll do is that we're going to use this description of a map on a surface. It's a multigraph with the order of incidences prescribed at every vertex. So I said it should be easier, so now I want to describe in those terms this map, and it should be, so now I don't have this underlying surface, I just know that there is a loop around every edge. I don't care anymore about planarity, I just have a multigraph. There's two edges between them. And then there's this final edge, which was starting in this corner, so that's what's important, and ending in that corner. And I had a root edge somewhere here. And so what this theorem is telling you is that this picture contains, as a map, just as much information as this thing that I had a hard time drawing. So what means this story of orders around the root, if, for instance, I take this out and draw it here, I will have a different map, because the permutation here will be different. Okay, so now the aim of this lecture here is to tell you how we can write an equation. So now we fixed the number of holes, and we have a series mg, which again depends on the size variable t, which is the sum over all maps of genus G. And I recall that the genus can be defined in terms of this picture only, that is in terms of sigma and alpha of t to the edge number. So for those of you who have followed the lectures last week, I want to give an exercise. I have no idea where it is. I won't solve it. Exercise. If we don't fix the genus and just want to count all maps by edges, this is not too bad. So the exercise consists in using stat approach to write a functional, and here it will be a differential equation for the series which counts maps irrespective of the genus. Here of any genus. And the idea here is you're going to take this stats recursion, you remove the edge, you look at whether what's left is connected or not connected. If it's disconnected, you have two maps on each side. And if it's connected, the question is, how do you describe the several ways of plugging the root edge to a new vertex? Okay, but that's not what we're going to do. What we're going to do is prescribe the genus, and this is much harder. Okay, so before I start with the higher genus, let me just remind you what we did for the case of genus 0. So we had this series M0, and we had three types of maps. The atomic map, that's the planar case. The case where the root edge was an isthmus, and then the case where it was not an isthmus. We had a finite face here and a map there. And in order to count those cases, we were forced to introduce a new variable. So m of t and y. And as always, I dropped the t. So that's m0 of y. Recording the outer degree. So we have y to the outer degree of the map. And so using these little pictures and considering what it meant to add the root edge somewhere around a smaller map, we had been able to write this now famous equation, atomic map, then the quadratic term coming from the isthmus case. And then we had convinced ourselves that the third case was taken into account by this term. Okay, so that was last week. So now let's try to see what happens if we consider the next case. So a map on the torus, on the usual torus, the one torus. So, well, certainly it cannot be atomic, because you would have a face that would not be homeomorphic. It would be a punctured torus, and it would not be homeomorphic to a disk. Can we have a bridge as the root face in a map? Yes, we can. Yes, we can. Okay, so we have a bridge and two maps, which I'm now thinking as embedded like here. So we want something of genus 1. So what's the condition on the two pieces? You take two maps, and you want to glue them. Sorry? Yeah. So one of them is planar, and the other has genus 1. So this can be checked, for instance, using Euler's formula, described in terms of permutations, or here in terms of faces and vertices. So this will give us some, so we have contribution T for the root edge, and then M naught of Y. We have the Y squared, accounting for the degree of the root face here. And we have a factor 2, because the planar piece can be to the right or to the left. Okay? Okay, then we are left with the cases in which when you delete the root edge, you just get one component. And so here I ask again, what is the genus of this component? You take a map of genus 1, you delete the root edge, what can happen? What's left in terms of genus? Yeah. So the genus can be 0 or 1. So if somehow, well, we'll describe the two cases. So maybe you have deleted a handle in your surface by erasing this face, or you haven't, and in this case you're left with something of degree 1, of genus 1, sorry. So more precisely, what may happen? So there's a case which looks like this one, where when you go backwards, so you start from something of genus 1, you take your root corner, you start a half edge here, and you attach it to a corner in the same face. So somehow you're crossing a face that was already in your map, and in this way, the genus cannot increase. So that's one case, and you can probably imagine that it will be taken care that's exactly the same construction. And this is this contribution. But now we have one more term in which you started from something planar and increased the genus. So what may happen? So I had this map. I have the root corner. I start a new edge. And instead of plugging it in some corner around the same face, I create a new handle in my surface and plug it here in some corner, which is not in the same face. And so if you count faces and so on, you realize that this increases the genus by 1. So if we zoom a little bit at this face, so say at degree 4, and there was the outer face here, and I have added an edge here. So that's my handle, which now creates a torus from something that used to be planar. And you remember that I have this additional parameter y, which is the degree of this outer face. And so now I need to describe in this augmented map the degree of its outer or root face. So I determine it by following the outer face. So that's what I'm doing here. So this is the root edge. Now I arrive at this corner. I go on following. And sorry, I arrive here. I follow the face. And I'm back here. So what has happened here, I have actually merged two faces, the former outer or root face and this little square, into a single face. So the new outer degree of the bigger map is the sum of the former outer degree. So this was M prime, the small map, plus the degree of this selected face, this is F, plus 2 for the two sides of this root edge. So let me summarize that. We have the first two cases that were the same constructions as in the planar case. But we also have a third case where the new root edge ends in a face that's different from the outer face. And in this case, I also have to record the degree of the face where my root edge has ended. Okay, so now how can I describe this in terms of generating functions? Here, what I have to do this construction, I have a map with a distinguished face here, F. And in this face, I'm going to pick a corner. So this tells you that in order to be able to describe this final case, what I have to do is to introduce one more series counting. So this map here, M prime, was planar. So we need, in one way or another, to count planar maps with a distinguished non-root face. So that's our F. And not only that, but we need to record the degree of this face F in order to describe in how many ways we can plug the root edge into the corners of this additional face. So distinguished non-root face, and then this must be weighted by the degree of F. Yeah. Because the case of the root face has already been taken care of here. So in this case, we're not merging two faces. We are in fact splitting the root face into a smaller face and this one. So it's really the case where F is different from the outer face that we need to consider here. Are there more questions on this case here? Yeah? Yes. Yeah, so that's the so-called cut and join equations by Goulden and Jackson, where they sometimes, I think, merge cycles and split cycles. That's what happens. So here you have these two former cycles which were, so in the cycles of phi, the phase permutation, you're essentially merging these two phases, and that's merging two cycles. Okay, yep, sorry? Yes, this works as well for bipartite maps. Yeah. Yeah, in general, many of these decompositions, as I say, they are fairly robust. So you could keep track of, I'm probably moving a bit too far, which is always the case when one answers your questions. But one could record phase degrees, the whole collection of phase degrees using this kind of construction. Okay, so now we are facing a new problem. We need to count planar maps, but with a mark phase. And can we convince ourselves that we could do it by recycling this construction? So here, well, there's no non-root phase, so we're done. Here, the marked phase can be on any side, but this will work quite nicely. And here, either the marked phase was already in the bin here, in which case we get something recursive, and otherwise it's this one that we want to mark, and we'll have to record its degree. So in this case, we'll split the degree of the former outer phase into two parts, one of the new outer phase and one of the marked phase. So, I mean, we'll do it later for general G, but it seems that probably we can write an equation for this generating function of planar maps with a marked phase. So now what I invite you to do is to consider the general problem, arbitrary genus G. Okay, so there will be this bridge case where you split your map into two maps of genus G1 and G2 that should sum to G. So here we had 0 and 1. There will be this case where you have just added an edge in what was the root phase. And if you delete this, you get something of genus G. And then there's the more difficult case where your root edge came from joining two phases, the outer phase and one marked phase, the degree of which you need to record. And so, okay, if you started from genus 2, now you want something of genus 1 with a marked phase. And you iterate that. Okay, now I want to count maps of genus 1 with a marked phase. So I remove their root edge, and I end up with, maybe in this final case, with a map that's now planar but has two marked phases, the degrees of which I have to record, and in which I will consecutively add edges. Okay, so if you chew this a little bit, you'll see that certainly you can write equations, provided you consider rather a whole family of generating functions. And so what we have to do to write a closed system is to introduce for every J a big series which, so I will very slightly lighten notation by dropping the T as before. So what is this? This is the generating function of maps of genus G. So far, so good. With k distinct non-root faces yeah. That's right. Thank you. This one I should keep. So you have, so they are ordered so that you can label them. Labeled 1, 2, k, and they are all distinct. And all these are counted, well, by edges. So that's my main variable t. You still record the outer degree, so the degree of the root face. That's, as usual, my variable y. And then, for every marked face, let's call them f1 up to fk, you record also the degree. So that's my marked faces. So this is recorded by the variables y1 yeah. Sorry? So if you just do genus 2, you'll need, so genus 2 with no marked face, that's what you are aiming for. So you will need genus 1 with one marked face, and inductively genus 0 with 2 marked faces. So here, this collection of series will allow you to get mg of ty for any g. Okay, so I hope I've convinced you that this is a good, big family of series to consider. If you prescribe the genus you are aiming at, you will only have to consider a finite number of them. For instance, if you are aiming at g equal to 2, then you just need m naught of y, y1, y2, m1 of y, y1, one marked face, and then this should give you, hopefully, this one. Okay? But I'm going to write the equations for arbitrary k and g. So that's probably an awful thing to do, but still it's doable, and as we'll see, it yields results on the generating function of maps of prescribed genus G. Okay, so I'm going to use a bit of notation here. For any subset of indices, I in 1, 2, k, I'm going to denote by yi the tuple of yi I j if I is equal to y1 less than y2 less than yj. Okay, and now what I want to use is just Tutt's approach. So let's be brave. So that's another notation. Well, I said I would use double brackets, so that's 1 up to k. Well, I guess first I should do the planar case. Okay. So in the planar case, I want an outer face and k marked faces and record their degrees. So the atomic map, I cannot have any marked face. So it only comes in the picture when k is 0. Okay. Now I am in, say, in the bridge case. So this is a map with a certain number, with k marked faces. I may have I on this side and k minus I on this other side. So I need to partition my set 1, 2 up to k into two subsets. I will put the indices of I here, and here the indices of the complement. So you really have to think of my maps as something like this with some distinguished faces. Okay? So maybe my isthmus was putting F1 on one side and F2 on the other. So let's go for the isthmus case. I have here T for the bridge, so far so good, y squared for the degree of this root face here. And then on one side, I put the series M naught of y and yi, but I need to sum over all possible i's. And then on the other side of the bridge, I have another planar map with marked faces indexed in the complement of y. So for instance, one term here, if I have two marked faces, could be m0 of y, y1, m0 of y, y2. But I would also have a term m0 of y, m0 of y, y1, y2, if both marked faces happen to be on the same side of my root edge. Yes? So here they have, well, you could imagine that you have infinitely many variables and you could write the same equations, yes. But here I find, I mean, in practice, when you have to solve genus 5, you just need finitely many variables, precisely y1 up to y5, because you'll end up at some point having to consider planar maps with 5 marked faces. So you mean in my collection of series, if I specialize? No, because I will kill, I mean here in this definition, every yj has a positive power. So I really have k marked faces in my definition. So yk will be there to some positive power, which is the degree of the face fk. So if I specialize yk to 0, I get 0. Sorry? Oh, yeah, I will get, the first order will be the case where the marked face is, has degree 1. Yeah, you're right, extracting the coefficient of y1. So then I will get, indeed, not a marked vertex, but a marked corner, where I put this loop, which is the kth marked face. No, it's not.
One of the y's is wrong.
Yeah.
What you're doing is not remembering the degree
of this marked face, but the marked face is still there.
the unmarked series because you don't have a fixed number
of faces. So if you would, in addition, record in your series the number of faces, this would be also differentiating essentially with the respect to the face variable. Okay, so that was the isthmus case. We've split our planar maps into two maps, each having possibly marked faces. And then we are here with this non-bridge case. So there's the simple case where all marked faces were already in the smaller map. And this is our favorite construction. I take a map now with marked faces, and with k marked faces, and then I add an edge in the outer face. So you can convince yourself that this is our favorite construction with this divided difference. So we've split the outer face into two smaller faces, or essentially smaller faces. Yeah?
On the right, you have y minus 1.
So first it's y minus 1. Is that what you're saying?
Yes, and then it's a plus sign.
A plus sign on the left.
The left of ty.
So that's a plus.
It looks more like a minus.
Not have to play or any other.
It's a plus, yes. And now we have to consider one more case where maybe one of the marked faces, the marked non-root face, say Fi. Why don't you have glasses? So there's one more case, unfortunately, where the marked face of this big map is the one that we have just created by adding an edge. And this can be any of the k marked faces. How unpleasant. Okay, but let's be brave to the end. So that's a plus for Philippe. So, as I said, this I can be anything between 1 and k. There's a t for the new root edge. So now what we had, this smaller map, it had k minus 1 marked faces. So let's take, so we are going to do as in the first lecture, we'll refine explicitly by the outer degree to see clearly what we have. So we call D the outer degree of this map. So how should I call this? So I want some M0D of y. So that's all indices except I. So what is this thing? This thing here is the generating function of planar maps. The outer degree is D, and then there are k minus 1 marked faces. Whose degrees are recording by y1, y2, but not yi up to yk. So this is not the end, so I take this series, and now, so I take So I will describe again what happens here. Okay, so this map is my usual bean. I used to call it M prime. The outer degree is D. It has a number of marked faces, say F1 and F3. And here, I want to create a marked face F2. And I need to record its degree by a variable y2, and I need at the same time to record by y the degree of the outer face. Okay, so I go on here. So starting from this M prime, so that's my usual thing. If I just create a face of degree 1, so I will get, say, a yi. So in general, this is fi, yi to the 1. And then the outer face has degree d plus 1. If instead, that was my first corner, if I create a face of degree 2, that's y to the 2, y to the d, and so on. So each time I choose a corner that's a bit further, I increase the degree of the marked face by 1 and decrease the degree of the outer face by 1. And the final case is when I add a big loop around M prime. So my final coefficient will be that the marked face has now degree d plus 1, and the outer face has just degree 1. Okay, so that's a refinement of what we had in the first lecture. Not only we are recording the degree of the outer face, but also the degree of this new face that we have created. So this is again a geometric series, and you can sum it. So this goes up to now yd, so it should be y d plus 1 minus y I d plus 1 over y minus yi. Again, so this is the weight in terms of degrees of outer face and new marked face of all the maps that I can construct from M prime. So I should add this term here. So there was y, yi, y d plus 1 minus yi d plus 1 over y minus yi. And now I can sum this. So it's fairly terrible, but it's just being stubborn, and at the end it works. So yk. So there's this simple case plus so that's not mg, sorry. We're not there yet. So that's m naught of y, yi, m naught of y, k minus I. Then there's the simple case where all marked faces were in the smaller map. Why did I copy that again? With a divided difference. And then the sum over I. So there was a t. There's a y that comes out. So And then what I get is y. So that's m naught. So here, with this term, I essentially have my original series, except that I don't have the yi variable. And then the other one so now, whereas in the definition I have y to the d, I have yi to the d. So I have specialized this outer face variable to yi. And then I have all the others for the marked faces. And this is now divided by y minus yi. Whew. Aïe, 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 comme dit Philippe.
That's just genus zero.
And that's genus 0. No handle. There will be one more term. So does it fit with what I have in my notes? Sorry? Yes, that's a yi. You're right. Thank you. Is that okay? Yeah? Okay. So we've written a bunch of equations, one for each k. So let's breathe a little bit and look at this. So first, when k is 0, no marked face. I've just written my favorite equation, the one we started with last week. Okay, now if I have some marked faces, that is k is positive, what do I see here? So maybe, so k equals 0, that's the usual equation. Which is quadratic because of the isthmus case. Not quadratic, but quadratic in m naught of y. And this one we've learned how to solve using this quadratic method or the recipe. So this one is algebraic of degree 2. Now, if k is positive, where in this equation do I have this series here that I'm trying to compute? So certainly it's in the left-hand side. Here, the bridge case, I get two terms that involve this series, either when I have no marked face to the left or when I have no marked face to the right. So say maybe here, so I could get some m naught of y, yk, times m naught of y. Okay. And I have a symmetric term. Okay, and all other terms in this sum, they involve series of maps with fewer marked faces. So of course, I'm thinking of computing this series by induction on k. So here I have two terms where I have my unknown series. But you see, I have no more quadratic term. Whereas when k was 0, I had in the isthmus case, one quadratic term. Then here, well, I have my unknown series here, and then its specialization at y equal to 1. So this has the same flavor as all our map equations. And here, I have Sorry? Yeah. Yes, if you record the number of faces. No, because these are rooted maps. So what are you suggesting? What do you call the coordinate? Or the variables that record there? Yes, I think you have such an identity. If you consider maps with two root corners. Yeah, exactly. So if you consider maps with two distinguished faces, and more precisely with two corners, two marked corners in two different faces, you end up writing an equation that indeed relates this series. Well, this is not what we're going to do. We are going to use this kernel method, or what we saw last time, but you didn't see last time, to get rid, or rather to determine this specialization first and then get back to this series here. So I go on with visiting the various pieces of my equation and looking at where my main unknown series occurs. So we have seen it here, here, and here. And here, well, I have just series of maps with fewer marked faces because of this k minus I here. So I can consider by induction that everything here is known. Okay, by induction. You don't seem to agree, but you seem relieved, so am I. So finally, if I group, when k is positive, if I group all the terms that involve my main series, I find that m naught, I'm trying to determine, times 1 minus, so I have two pieces here, 2, that's a 2 t y squared m naught of y. So that's the isthmus case. Minus t y minus 1. So that's this. Thank you. Is equal to some known terms. For Frédéric, I'll put, I don't know how they are called. And then you have this specialization, t, y, m naught of 1 and yk over y minus 1. So what I'm saying here is that once you've solved the k equals 0 case, as we did last week, you end up here with an equation that is slightly simpler because it's linear in the main unknown series. Of course, you still have this difficulty that in the right-hand side occurs one specialization of the series you are hunting for. Okay, but in principle, that's the moment where we have to apply our recipe. So this is a polynomial in one main unknown series, one auxiliary series that doesn't depend on y, and many things that we know. So the recipe says, okay, you have to look or to cancel the derivative of this thing with respect to the main unknown series. And so what we were asking is if there exists some y of t such that, well, such that the derivative with respect to that, but this is just this thing here. That's little y. And there's the wrong sign. You're right here. But in fact, we've already asked the same question when we were solving the original equation, which is here. When we were applying our recipe to this case, we wanted the derivative with respect to this to be 0, so we were writing that 1 should be equal to t y squared m0 of y plus t y squared over y minus 1. And so this is closely related to the form of our equation. The solution y of this equation we've already met. Okay? And so we know everything about it. We have an expression. It's a quadratic series in T because we've solved that already. So now, if we plug this value of big Y in this equation, well, we are just canceling this term. So this is a very special version of this general recipe. We are just canceling this. So this tells us that Ty m naught of 1 over y minus 1 must be something that we know already. Okay, and so and then you will determine this one and then back to that one. So this y, so there it exists and it's some rational function in, well, what we have for maps usually, square root of 1 minus 12t. And so I spare you the details, but using that, you can, well, first you can do it in practice. That is for small k. You can compute inductively this series m naught. And then you can also see that that you'll get, once you specialize thing at 1, you'll get series in the same that are always rational functions in 1 minus 12t, square root of 1 minus 12t. Okay, so if I have to summarize, so I want to summarize what we've done so far. We've just considered the planar case, bad news. But I hope that I have convinced you that these equations can be solved by induction on K using this recipe, that is by canceling this term, which happens to be the same for any K. That's a good point. And this will allow it to compute us all this series M naught. And now we have to take the final jump into arbitrary genus. So where am I going? So it parallels this, except that you have one more case, the case where the genus increases. Yeah. So I think thank you. It's a good observation. You're entitled to one more question then later. Okay, and now G. This is not a factorial. Okay, so what will happen if we try to apply this to compute mg of y, and you have k marked faces? How horrible will it be? In positive genus, you have no atomic one. Isn't that simple? OK. So in this case, I have to do two things. I have to split my set of marked faces, some to the right, some to the left, some to the right, some to the left, and I have to split the genus. Let's split the genus. So a sum. So I split the labels of the faces, and I want, say, some G1 and G2 that sum to G. And then I put all my pieces together, so I have a Ty squared for the bridge. And then I simply have some mg1 of y, y, I, and mg2 of y, and then the complement k minus I. Okay, and now come the maps, such that when I remove the root face, I just get one piece. And this piece can have either genus G, if I've just inserted my new edge in a corner of the root face, or G minus 1 in the handle case. So we'll first deal with the case where the smaller map has genus G, because as you can imagine, it completely parallels what we have here. And I can, so there's the, so now, so I repeat, my smaller map has still genus G, and first subcase, the small face that I have created here is not marked. So that's, well, the usual construction. So T, Y, Y, mg of y, yk minus mg of 1, the specialization, yk over y minus 1. Then next case, the genus remains the same, but the small face I have created is one of the k marked faces. So that's the counterpart of this sum, except that we are now in genus G, but I just have to replace the 0 by a G. So I have fewer marked faces here. Okay, this is a shortcut. And then in positive genus, there's just one more case. That is, when we delete the root edge, we are left of something of genus G minus 1. That is, going the other direction, we've merged if we start from the smaller map, we've merged its outer face with one marked face, and together they have become the outer face. In particular, this marked face where we've put the end of the root edge is not one of the FIs, because then it will become the outer face, and the outer face is not marked. So this tells you that we have to start from a map of genus G minus 1 and K plus 1 marked faces. And in the K plus 1th, we'll attach the endpoint of the root edge. Okay, so that's, I guess this has completely disappeared. Couldn't you warn me? So that's the case where the genus increases. So let me remind you of this little picture. We have some K plus first marked face here. We start from the root corner, and we add one root edge here. And so I had written that the outer degree of the big map was 2 plus the degree of the marked face plus the outer degree of the smaller map. And then we shouldn't forget that we have more marked faces here. Okay, so here the genus decreases, but the number of marked faces increases. Okay? So what should we do? So, well, we have a new edge. We have a map of genus G minus 1. We still record its outer degree. There's a y squared here. Now what should I do? So it's counted by y1 up to yk, which account for these things. And then I still want to select the corner here. So does it mean that I have to differentiate with respect to yk plus 1? I'm afraid this is what I have to do. Yeah, so not only I have to mark one face, but I have to tell in which of its corners I will arrive here. So here I have a variable yk plus 1 up to the degree of fk plus 1, and the number of corners is the degree. So I need to differentiate this series with respect to this k plus first variable. And then I specialize this because the degree of fk plus 1 will now count in the degree of the outer face. So I have to specialize this when yk plus 1 is y. Say that again. Here, because I'm losing, you're right, I need a cube. Thank you. Check if I had the cube in my notes. Yeah. Sorry, can you?
I would like it better to have
Y squared times. Well, okay. Yeah. Should we do this for Philippe? I need to have one more parenthesis to tell you where the, yeah, I could put it here. If that's the only problem, then we're in business. Okay, we're done. We've written one more equation, and I promise it's the last one. So now I'm going to play the same game as before. So formally, we had this induction on the number in genus 0, on the number of marked faces. So here, let's look at, well, the main series. Where is it? So it's on the left-hand side. It certainly occurs here when you take one of the two genuses to be 0 and all faces in the component of genus G So you'll have so maybe I'll do the same thing as before. So we have our main unknown series. So times 1. And here we have minus 2t y squared. So the 2 comes from putting the planar part to the right or to the left. So say that's something here. Then certainly all this term just comprises our main series. So minus t y squared over y minus 1. And I'm closing my bracket for reasons that you'll understand. So here to the right, I have at some point the main series specialized at 1. And then here, well, I have series that involve one less marked face, so which can be known by induction. And here the genus is smaller, so I could also compute this by induction. So plus something that is known. Horrible. Yeah, if you know mg minus 1, according to all its variables, you can differentiate, and it will still be something algebraic. And here, you can admire that I still have the same function that was defining my y of t. So I will stop here with these equations, but this you can solve again by replacing little y by this y of t, and this will give you an expression of this specialization in terms of known things, and then you can get back to that and obtain your equation. And so that's what Bender and Canfield did. And here are two of their results. By looking at this procedure, they were able to conclude that for any g, the generating function of maps counted by edges is something algebraic, and more precisely, it's a rational function of 1 minus 12t. So you remember in the planar case, we had a 1. Yeah, thank you. We had 1 minus 12t to the 3 halves, and then a fraction in that. So this persists. And then they were also able to determine essentially the form of the singular behavior of this series near when t approaches 1 over 12. And so the second part of the result that I want to cite is that, again, for g fixed, the number, say, mg of n of maps of genus G with n edges behaves, and by this I mean as n goes to infinity, as some constant famous constants, usually denoted by Tg. So that's 12 to the n to the minus 5 halves of g minus 1 for some positive Tj. And they were also able to compute the first of this series. So these are 30-year-old results. And since then, there's been many developments. And in particular, I just want to say that more is known about these numbers and about the TG. So those of you who were attending the first workshop 2 weeks ago heard Guillaume's talk on these numbers TG. So I just want to tell you a little bit these very nice things that have been done since then. So we skip many years. So first I want to tell you that more is known about the numbers Tg. So first they are now, so computing them using this approach was something terrible because you need to inject some constants for all these maps with marked faces and understand what should be the asymptotic behavior of their number, and you'll get something horrible describing recursively a much larger family of constants, essentially some T, J, K, and whatnot. But now, so if we rescale Tg by introducing tau g, which is 2 to the 5g minus 2, then there's the gamma function over 2. First one. Is that the correct? I'm not sure suddenly about this. That's the correct one. Okay. That's the usual game between the exponent in the coefficients and the exponent in the singularity of the series. So you multiply this by Tg. Then you have some recurrence relation that tells you that tau g is a third of 5 times the previous one plus a convolution term plus some initial condition. And so who came with that formula first? I've written Bender, Gao, and Richmond, but there's earlier references. Yeah? Yeah. So the one I have here follows a paper in the combinatorics literature, but this is being unfair, obviously. Gao, Richmond. And this follows from a recurrence relation for the number of, I think, triangulations in genus G, which I'm not going to write. But what I'm going to write is something very amazing, a recurrence for these numbers, which is due to Guillaume Chapuis and Carroll. What's his first name? Sean Carroll. So that's something wonderful, but that we have no combinatorial understanding of at the moment. So forget about these horrible equations. So that's much more recent. A theorem by Sean Carroll. So how many R's and L's? 2 and 2. And this appeared 2015. So I'm still using the same notation, mg of n, maps in genus G with n edges. And these numbers satisfy a simple recurrence relation. From which we can compute them much faster than with the Bender and Canfield equations. So the genus decreases here, as well as the number of edges, and then you have some big convolution. So you want K and L sum to n, and both are positive. And you also have a convolution in the genus. And of course, yeah, both are non-negative. And you have a term symmetric in K and L, and you have the two pieces. There we are. Damned, as you say. So the TG is the constant. Sorry?
So tau G is given by TG. You have it mg.
So mg is the number of maps. That's the actual numbers. This is just asymptotics results, and this is exact results. A procedure to compute. Yeah. So this comes from the fact that these map-generating functions satisfy certain differential equations known as the KP hierarchy. This is a wonderful formula. We have no combinatorial understanding of why this should be true. But still, it gives one more proof of that, for instance, but it is stronger because it's finer. It's exact information on these numbers. And yeah, so this is a wonderful formula on which, I am a little bit early, okay, so I won't stop right now. So that's, so I've skipped something like 40 years. Yeah, 40 years. So this is somehow the state of the art on these numbers of maps with counted by the size. So there's been a lot of work done since Bender and Canfield, but this is not combinatorially understood at the moment. Yeah, you have a question? Yeah, so you have an underlying differential equation here, yes. Well, I guess if you normalize by a power of g factorial, that is, you get some exponential generating function, then this one should converge. Are there more questions on this higher genus? That will be my only high genus moment in these lectures. Yes? Mm-hmm. Mm-hmm. Possibly. What should I say? Well, it's not obvious to come with this for a start. Well, in MG, it's not so bad because in MG it's linear. Well, you also have some terms here, but it will be linear for higher genus. So yeah, you could do some, maybe you could have guessed that, and then maybe you could try the same kind of procedure to guess number of maps with marked faces, prescribed genus. Help yourself. Yeah? Maybe Guillaume wants to do that. Did you try? No. Yeah. Okay, so I have, well, maybe 10 minutes left. I don't want to start something new, so I will still give you a few more things on this method. So what did I skip? So there's several things in my notes that I skipped. So what was it? Maybe we can end with an exercise, if you're not dying. So I told you that in the first lectures, we would only deal with maps that carry no structure. Okay, I said that. This one I keep, it's so nice. There's at least one counterexample to this statement. That is a problem of maps carrying some additional structure, namely a configuration of hard particles that can be described by such equations and thus has an algebraic solution. And so maybe that's the last thing we'll discuss today. So it's a model of hard particles on planar maps. So you have a planar map. With a root corner. And some vertices carry a particle, say a green particle. But there is a condition, well, that's hard to fulfill here. So these particles are hard in a sense that when you have two neighbor vertices, they are not allowed to carry both a particle. Okay? And I claim that for the generating function of maps with a hard particle configuration, you can write equations with one catalytic variable, provided you consider the correct catalytic parameter. So there will be two series, say f of y, or it's always t and y, and g of t and y, which will be respectively the generating functions of maps with hard particles counted by the edge number as arrays. And here you want y. You're not counting the outer degree, that is the number of corners. You're just counting the number of white corners, that is the corners with no particle. So how should I call it? The white outer degree. So that's the number of corners in the root face with no particle. And so this is for M where say the root is white. So that is carries no particle. And here you have a particle at the root. And then the parameters are the same. Sorry? What? Yeah, it's still, so there's just one catalytic parameter, the number of white corners. Yeah, this could be 0. Oh, yeah, so only in the atomic case it will be 0, when you have just one vertex. You're right. Okay. So f of y. So as I say, we have the atomic case, and then there are isthmuses, bridges, and the usual case. So here I have God knows what. And then for G, there will be something similar, except that now I have a particle at the root. And so here I know that I can't have any particle. And then green particle, root face. Okay, so maybe we can start with G, and here I would like to hear you. So following these little pictures, what can I write? This one. Yeah. So this, okay, I don't want to insult you, so that's a 1. I could also put weights for particles. Maybe I put an S per particle. Why not? So this is making life more interesting here, because then I can try to see what's the density of particles in my map and so on. So here, what do I get? Sorry? There's an F and an G with a Y each time. The number of white corners, they are essentially additive. We have to adjust something. Sorry. So,
root corner on the left.
Yeah, so there should be a y, because there was just in this piece, here there was one white corner, whereas now that I've added the edge, there's two white corners. So I get a factor y, okay? And then here, well, I'm just taking a map with a particle at the root, and I create a new edge which must end at a white corner. So that's why it's good that my y is recording the number of available corners. So there's a t, and then if the outer degree is d, I have here, so it's a g with outer degree d, and what can I do? So I'm aiming at something white, and so what is the number of white corners in what I'm creating? So if I go to the first corner, it probably doesn't change. And if I go to the last white corner, so I do something like that, I'm left with just one white corner. Okay, so that's an equation for G. 1 plus T y, f of y, G of y, plus T y, and I have G of y minus G of 1 more divided difference over y minus 1. The first term is an S. C'est vrai. Okay, so that was for the case of a particle at the root, G. And now for F, there is a little trick. Well, clearly here, at the other end of the root, you may have a particle. But then if you flip the root edge, what you have is just a G. So what's really the decomposition that I'm writing here for F is, okay, I can have an atomic map. Then I have the case where the other end of the root edge contains a particle, and then here anything can happen. And then I have the case where the root edge has two empty ends. Okay. So here I get a 1. Here it suffices to declare that my root edge, instead of being like this, is like that. That is that the root corner is here, and this is just G. Sorry, it's G minus S, and then in addition, I should probably root here rather, so that the number of white corners remains the same. So anyway, I have G of y minus S. So this is the little trick that prevents you from having to record the number of black corners. And as soon as you decide to record both the number of white and black corners, or white and green corners, you have to record how they are interleaved, and then you are in a terrible trouble. So that's something you don't want to do. And then here I am safely with that. And here this is similar to what was happening here. Maybe I should be careful, because then you can have loops. So T. So I take a map of outer degree D, and what can I do? So I can create a small loop here, which should increase by 1 the number of white corners. So it's just a bit different. You have one more case than you had here. Okay, so I won't go further, but I just wanted to mention that this is one of, I think, the few models of maps with some structure that you can address using a single catalytic variable, address and solve. So you have a system of two equations. So if you get rid of one of the unknown series, you'll still have two of these auxiliary series that do not depend on y. But you can do things. I should add that this observation that you can write is in fact due to Gilles Schaeffer, that you can write equations, and that we studied this system in our paper with Arnaud Géane. Okay, and this time I'll stop here, and I'm happy to answer questions if we have some. Next time you'll get bijections. That will be a bit more relaxing.